The universe holds many mysteries. Black holes are some of the strangest. Imagine a place where gravity is so strong that nothing, not even light, can escape. This is the essence of a black hole. The idea of black holes has been around for centuries. As early as the 1700s, scientists like John Michel and Pierre-Simon Laplace pondered the existence of dark stars so massive that their gravity could trap light. However, it was Albert Einstein's theory of general relativity that provided the foundation for our modern understanding of black holes. Einstein's theory, published in 1915, revolutionized our understanding of gravity. It described gravity not as a force but as a curvature of space-time caused by mass and energy. Einstein's equations predicted the existence of objects so dense that they would warp space-time infinitely, creating a gravitational singularity. These objects, from which nothing can return, were later termed black holes. The concept of black holes remained largely theoretical for several decades. It wasn't until the mid-20th century that astronomers began to gather observational evidence to support their existence. Today, black holes are no longer just theoretical constructs. They are now recognized as fundamental components of our universe, playing a crucial role in the evolution of galaxies and the cosmic web. Stars are the cosmic furnaces where elements are forged. They are born from clouds of gas and dust, collapsing under their own gravity. The intense pressure and heat at their cores ignite nuclear fusion, powering the star for millions or even billions of years. However, even stars have a lifespan. When a massive star exhausts its nuclear fuel, it can no longer support its own weight. The core collapses inward and the outer layers are ejected in a spectacular explosion known as a supernova. If the core remaining after the supernova is massive enough, typically several times the mass of our sun, gravity will continue to crush it. This relentless collapse compresses the core beyond its physical limits. It shrinks to a point of infinite density, forming a black hole. This process of stellar collapse is the most well-understood mechanism for black hole formation. However, scientists believe that black holes might have also formed in the very early universe. These primordial black holes, as they are called, could have originated from density fluctuations in the hot, dense soup of particles that existed shortly after the Big Bang. Unlike their stellar counterparts, primordial black holes could have a wide range of masses, from microscopic to billions of times the mass of our sun. Imagine approaching a black hole. As you get closer, the gravitational pull becomes increasingly intense. You would feel this pull more strongly on your feet than on your head. This difference in gravitational force, known as tidal force, would stretch you out like spaghetti, a process aptly called spaghettification. At the heart of a black hole lies the singularity, a point of infinite density and zero volume. Here, all known laws of physics break down. Surrounding the singularity is the event horizon, the point of no return. Once you cross the event horizon, there is no escape. Not even light, the fastest thing in the universe, can escape the gravitational pull within this boundary. The event horizon is not a physical barrier but rather a region in space-time where gravity is so strong that all paths lead inward. The size of a black hole is determined by its mass. More massive black holes have larger event horizons. The distance from the singularity to the event horizon is called the Schwarzschild radius, named after Karl Schwarzschild, who first derived this solution to Einstein's field equations. For decades, black holes were thought to be completely black, swallowing everything that crossed their event horizon and emitting nothing in return. However, in the 1970s, Stephen Hawking revolutionized our understanding of black holes with his groundbreaking discovery of Hawking radiation. Hawking showed that black holes are not entirely black after all. They actually emit a faint thermal radiation due to quantum mechanical effects near the event horizon. This radiation arises from the creation and annihilation of virtual particle-antiparticle pairs near the event horizon. Sometimes one particle falls into the black hole, while the other escapes, carrying away some energy from the black hole. This process, known as Hawking radiation, gradually reduces the mass of the black hole over time. Hawking's discovery had profound implications for our understanding of black holes and the nature of space-time. It linked gravity, quantum mechanics, and thermodynamics in an unprecedented way, giving rise to the field of black hole thermodynamics. However, the extremely weak nature of Hawking radiation makes it incredibly difficult to detect directly. Scientists are actively searching for observational evidence of this faint glow. Section 5. Matter's dance, accretion disks, and energetic jets. Black holes are often depicted as isolated objects lurking in the darkness of space. However, in reality, they are often surrounded by swirling disks of gas and dust, known as accretion disks. These disks form as material from a nearby star or a gas cloud spirals inward towards the black hole. As the material falls toward the black hole, it gains tremendous speed and heats up due to friction, emitting intense radiation. This radiation from the accretion disk is what makes black holes detectable, even though we cannot see them directly. In some cases, the infalling matter is channeled by magnetic fields near the black hole, creating powerful jets of particles that are ejected at nearly the speed of light. These jets can extend for thousands of light years, influencing the evolution of galaxies and their surroundings. The study of accretion disks and jets provides valuable insights into the feeding habits of black holes and their impact on the surrounding environment. By observing the radiation emitted from these structures, astronomers can infer the properties of the black hole, such as its mass, spin, and accretion rate. Section 6. Warping spacetime, the gravity of black holes. Black holes are the most extreme objects in the universe. Their immense gravity warps the fabric of spacetime in their vicinity. This warping of spacetime has profound consequences for the way we perceive the universe around a black hole. One of the most striking effects is gravitational lensing. When light from a distant object passes close to a massive object like a black hole, its path is bent by the curved spacetime. This bending of light can create multiple images of the background object, as if it were viewed through a cosmic lens. Gravitational lensing is a powerful tool for astronomers. It allows us to study distant objects that would otherwise be too faint to see. It also provides a way to map the distribution of dark matter, an invisible form of matter that makes up a significant portion of the universe's mass. Section 7. The Information Paradox, a Cosmic Conundrum. Black holes present us with a profound paradox that has puzzled physicists for decades: the information paradox. According to quantum mechanics, information about the state of a system is always conserved even during a physical process. However, the classical picture of black holes suggests that information that falls into a black hole is lost forever. Once an object crosses the event horizon, it is irretrievably lost to the outside universe. This apparent loss of information violates a fundamental principle of quantum mechanics. The information paradox highlights a fundamental incompatibility between general relativity and quantum mechanics, the two pillars of modern physics. Resolving the information paradox is a major challenge for theoretical physics. Some proposed solutions suggest that information is not truly lost, but rather encoded in subtle correlations within the Hawking radiation emitted by the black hole. Others explore the possibility that our understanding of black holes is incomplete and that new physics, perhaps in the form of quantum gravity, is needed to fully describe them. Section 8. LIGO's Symphony, listening to the echoes of black hole mergers. For centuries, our understanding of black holes was based primarily on theoretical predictions and indirect observations. However, in 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, made a groundbreaking discovery that revolutionized our view of these cosmic behemoths. LIGO detected gravitational waves, ripples in the fabric of spacetime, produced by the merger of two black holes located over 1 billion light-years away. This historic detection not only confirmed Einstein's prediction of gravitational waves, but also provided the first direct evidence for the existence of binary black hole systems. Since its initial discovery, LIGO has detected numerous other black hole mergers, along with mergers involving neutron stars. These detections have ushered in a new era of gravitational wave astronomy, allowing us to study black holes and other extreme objects in unprecedented detail. Section 9. Uncharted Territories, Black Holes and the Future of Physics. Black holes remain one of the most enigmatic and captivating objects in the cosmos, pushing the boundaries of our understanding of the universe. They are cosmic laboratories where the extremes of gravity meet the quantum world, offering a unique testing ground for fundamental physics. The study of black holes has already led to groundbreaking discoveries, from Hawking radiation to gravitational waves. As we continue to probe the mysteries of these cosmic behemoths, we can expect even more surprises and paradigm shifts in our understanding of the universe. Future research endeavors, such as the Event Horizon Telescope, promise to provide even more detailed images of black hole shadows, testing Einstein's theory of general relativity in extreme gravitational fields. The search for primordial black holes could shed light on the early universe and the nature of dark matter. Black holes will undoubtedly continue to captivate our imaginations and inspire scientific inquiry for generations to come. They are a testament to the vastness and wonder of our universe, reminding us that there is still much to explore and discover.